Hi, this is Koen. Can you all hear me? Okay. I'm not sure why I'm having this weird background, but I'm currently in Belgium. And today, something went wrong. Today we have Hannah Heynderickx. Although we are from the same country, which is Belgium. She is currently in New Zealand, and she is doing research investigating ocean acidification and climate change. And we are really delighted to have her today. And so, Hannah, thank you so much for doing this presentation. And the floor is all yours.
All right. Thank you so much. And thank you so much for having me. I'm very excited to be a part of this. So as Koen said, I'm currently doing my PhD at the University of Otago here in New Zealand. And I'm studying the impacts of ocean acidification on phytoplankton and bacteria interactions. And that's what I'm going to talk to you guys about today a little bit, and also how that relates to climate change. So let's get started. So probably all of you guys know already that climate change means an increase in the global average temperature, mainly due to anthropogenic or human-induced greenhouse gas emissions. And when we talk about climate change, most reports always compare it to industrial levels. And that's because in the industrial levels, or before the industrial levels, that means before humans actually started producing or started burning the fossil fuels. And on the graph that I've put up here, you can see that the arrow here shows us that there is an increase of 1 degree Celsius, and that is compared to these pre-industrial times. So today we have increased our global average temperature with 1 degree Celsius. Now, that doesn't seem too much, but if you look at our past or at our history, then we see that it only took 1 to 2 degrees decrease in temperature to drop into a little ice age. And it only took about a drop of 5 degrees in Celsius to cover the whole of North America with ice. Now, if that doesn't convince you enough, then just look at your own body temperature, because it only takes like an increase of 1 to 2 degrees in Celsius to cause a fever in your own body. So even though the temperature might seem small, it will have a huge impact on our organisms and ecosystems on Earth. And I've also put some long-term temperature goals. So all the countries have signed a treaty basically that says that we want to reduce, or we don't want our global warming to exceed 2 degrees in Celsius, or even to exceed 1.5 degrees in Celsius compared to those pre-industrial levels. However, we've already increased 1 degree in Celsius, so we're going to have to do a lot of effort to make sure we reach those goals. Then, how do we get this increase in temperature? Well, for that, I'll explain you the greenhouse effect. So when we get our energy from the sun, so the solar radiation, that will pass through our atmosphere, and that will heat up the Earth. Some of that radiation will get bounced back into the atmosphere because it gets reflected by the clouds, or it gets reflected by snow cover. But the solar radiation that gets absorbed by the Earth gets converted into heat, and that heat converts into infrared radiation that gets re-emitted back into space. Oh, yeah. But because we have this cloud of greenhouse gases in our atmosphere, that means that some of that energy will get absorbed by these gases and will get re-emitted back to Earth, which causes our Earth's surface to warm. Now, in the first instance, this is not a bad thing, because we do need a couple of those greenhouses in our atmosphere, because if we wouldn't have them, then our average temperature today would be -80 degrees, which would be very, very cold to live in. But because the human greenhouse gas emissions that we have been putting in our own atmosphere, that has caused the enhanced greenhouse effect, and that's why we see the increase of 1 degree temperature today, which that should actually not be there, and that just brings out our Earth's energy budget out of balance. So which are the greenhouse gases that we see in our atmosphere? Well, we have water vapor, carbon dioxide, methane, nitrous oxide, and ozone. But the greenhouse gas that we mainly all hear about in relation to climate change is the carbon dioxide. And why is it so important? Well, it's the main gas that we actually emit. And also because it has the longest lifetime, which means that it stays in the atmosphere the longest of all the gases. So that will be up to 100 to 1,000 years where it stays in the atmosphere. And then because it gets taken up by plants or it gets taken up by the ocean, it will leave the atmosphere again. Now, what are some of the sources of the greenhouse gas emissions that we humans are responsible for? That are the burning of the fossil fuels, transport, deforestation, and agriculture. And this is a graph that shows you what the contribution is of each of those sectors on a global average. So you see that energy supply accounts for the biggest part of the emissions, followed by the industry, the transport, and the agriculture. You have to remember, though, that this is on a global scale. So if you would look at it per country, you'll see that it will differ slightly. So for instance, for New Zealand, agriculture is the main contributor to those emissions. While if you look at the US, you'll see that it is transportation that has the largest contribution to that. Now, I'm sure you guys have seen a lot of the impacts of climate change during the past couple of weeks. So we can basically split those impacts up in the natural system and the human system. And the natural system, climate change will increase the extreme weather events, such as the droughts, increased rains, more wildfires, and the melting of the ice sheets and the glaciers. But then if you look at the human system, what mainly is going to happen, negative effects for food provision for like agriculture, where you'll get diseases in crops or you'll get bad production because of more droughts or less water availability. Then fisheries, the production will probably decrease because the population number of the fishes will decrease in the ocean. And then we also have like, there's going to be a possible increase of vector diseases. What I mean by that is, for instance, you see the picture of the mosquito there? Well, that mosquito is a carrier of a virus that normally only happens in Africa, but because of climate change, we'll see temperatures increase in the northern of Europe. So that mosquito now can migrate all the way up to Germany, for instance, where this year we have seen one case of that virus infected a human, and that normally has never been reported in Germany at all. And then the last thing is in the human system is that we will have to start protecting our vulnerable communities, as in, for instance, the coastal communities or the island communities, because they are prone to sea level rise and floods. And then what I'm mainly interested in is the relationship between the ocean and climate change. And there are 3 levels on which they can affect. The first one is the increase of the sea surface temperature. The second one is the ocean acidification. And then the third one is the reduction in the oxygen in the ocean. So what I will talk about is ocean acidification. Okay. So what is ocean acidification exactly? It is the long-term decrease in seawater pH because of the increase in the atmospheric CO2 that we have. And so far, since the Industrial Revolution, we have seen that our pH levels have dropped from 8.2 to 8.1. Now, it seems kind of hilarious because that is only a decrease of 0.1 unit. So you would think like, why would we care? But you have to remember that the pH scale is a logarithmic scale. So what that means is that decrease in only 0.1 unit actually means that we'll get a 30% increase in ocean acidification. So it doesn't mean that our oceans are acidic yet. It just means that if you look at the little pH scale that I drew here, it means that we'll get more acidic, so the pH will shift to the left. And this will have implication for marine organisms, definitely for the calcifying marine organisms, because they need carbonate, calcium carbonate, to build up their shells and their skeletons. So you can see on the pictures here on the left, you see a picture of corals where over time, because of the increase in sea surface temperature and because of ocean acidification, the corals have died off because they were unable to keep up their skeletons. Then the other picture here is of a sea snail. And here you can see that their shell actually starts to dissolve because of ocean acidification. And then another part is actually not only the shells and the skeletons, but also non-calcifying organisms can feel an effect because they will have to put more energy into keeping their internal biological balance, which seems like a big word, but basically means because the environment around them is changing in acidity, they have to put in more energy to work towards keeping their internal acid basic balance they have to keep it balanced comparison to their environment to keep their processes for growth and reproduction working. But if they have to put more energy into keeping that balance, that means they have less energy to actually use for growth or for their metabolism or for their reproduction. So in the early life stages, such as the larval stages, this will become very problematic. Now, I'm going to give you a quick overview of the chemistry that actually happens in the ocean because of ocean acidification. So in a normal scenario, don't be freaked out. It seems a bit complicated, but I'll take you through it. So in a normal system, we take up CO2 from the atmosphere that will react with the water molecule and it will create carbonic acid that is very unstable, so that will dissolve directly into a free hydrogen and in bicarbonate, and that can further dissolve in another free hydrogen and carbonate ion. And it's this carbonate ion that calcifying marine organisms use in combination with calcium to build up their shells or build up their skeletons. The ocean is known to be a buffering system, so what that means is that this reaction can go either to the left or to the right to keep their balance. So now what happens in the situation of today where we get ocean acidification? We'll get an increase in atmospheric CO2, which means the ocean will take up more CO2 as well. And that will mean we'll get an increase in those free hydrogens, but also in carbonate. However, as I told you, the ocean is a buffering system, so it doesn't want to increase these free hydrogens because that means it will lower the pH and you will create acidic environments. So what it does is it shifts the reaction back to the previous step where you'll create more bicarbonate and only one free hydrogen. So it can buffer out a little bit of the acidification. However, by doing this, it will also get rid of the free carbonate. And that's why it gets complicated for the organisms, because now this will not be available anymore. So they get in trouble because they don't have enough carbonate to keep making their shells or skeletons. Now, these are a couple of the New Zealand projects that have been going on to research ocean acidification. One big one is the CAREN project, and that stands for Coastal Acidification. The rate of it, the impact of it, and how we can manage it. And they specifically focused on 3 species that are very important here for the New Zealand industry. And this is the snapper, as you can see here, the green-lipped mussel, and the powwow or the abalone. And what they did very different set of experiments where they looked at how ocean acidification affects larval settlements. They looked at how ocean acidification affects food of those species, how it would have an effect on the different life stages, and also how maybe they can actually precondition the larval to future ocean acidification conditions so they would be able to adapt better. And this project has just rounded up, so I'll be very interested in seeing what the results are from these projects. Another two projects that are going on here are actually long-term time series. One of them is the Munida, where they have been measuring the pH measurements of seawater for the past 21 years. And then another one is at Beringhead, which is a place in Wellington, where they measure atmospheric CO2. And both of those time series are the longest ones in the Southern Hemisphere. But there are also time series that we have in the Northern Hemisphere that are actually longer than those down here. And I quickly added two graphs of some of those time series that look at the atmospheric CO2. And what they show us clearly is that you can see an increasing trend in both of those time series that measure the atmospheric CO2. And that just tells us that indeed our atmospheric CO2 is rising because of our greenhouse emissions. And I've put a couple of numbers in there. So today we have a level of 408 parts per million CO2. If we compare it to the pre-industrial levels, so the time before we started burning our fossil fuels, it was 280. And if you compare that to the levels that we had during ice ages, then we get to 185 parts per million. So you can see that it's a very big difference. Okay, now what I do for my project here is work on phytoplankton and bacteria. Now, what exactly are these? They're amongst the smallest and the most abundant organisms that we can find on Earth. Phytoplankton is very important because they account for about 50% of the oxygen that is present in the world. And both of the microorganisms you can find at the bottom of the marine food webs, where they're very important for a lot of nutrient cycles. And you can compare them actually to your gut microbiome. So inside our gut, we have a lot of bacteria present there that we need to keep our gut healthy and to basically break down our foods as well and get nutrients from there. So this is also what they do in the ocean. So I made this very simplified marine food web. Although I say simplified, it still looks a bit intense, but it shows you the interactions between phytoplankton and bacteria. So what they do here is the phytoplankton takes out CO2 from the atmosphere through a process called photosynthesis. Then they calculate, or they incorporate CO2 into their cells. And when they die, or through other processes, when they get grazed upon by zooplankton, they create this organic matter. This organic matter in the ocean can be taken up by heterotrophic bacteria. And these bacteria then use that as an energy source, but they can also use it for respiration, by which a part of the CO2 gets put back into the atmosphere. They can also use this organic matter to create inorganic nutrients that can be used by other organisms in the ocean, such as fish, for example. But they can also, again, be grazed upon by zooplankton. And then parts of bacteria, well, of course, bacteria will die then, and they can just sink out into the ocean. And of course, the organic matter that doesn't get taken up by bacteria can also, again, sink out into the ocean. And then it just gets stored into the deep ocean. So I know that it already sounds very complicated, but this is a very simplified model of what happens at the bottom of a food web. So if we would get interruption or disturbance at this part already, at the bottom of the food web, it would give great consequences throughout the whole food web. So through higher trophic levels, like fish or sharks or dolphins that actually depend on these phytoplankton and bacteria at the bottom of the food web as basically their energy source. So one of the projects that I worked on that I told you about, the Munida transects. So I said it's the Southern Hemisphere longest running ocean record of pH measurements. And this year we celebrated its 21st birthday. So it's a pretty big thing. What we do is we take the boat and we go out every 2 months and we collect a lot of different samples. We're very lucky here in New Zealand that we have off the coast in just a transect, so in a basically a vertical way that we go out, as you can see here, we actually cover 4 different water masses. So it's a very unique system. For my project, I want to look at the phytoplankton and the bacteria along this transect, and I'll see if how they change or how they stay the same on an annual time scale. So I've had data for the past 4 years. So every 2 months, I take samples along that transect, and I've had it for 4 years now, so I can look at how these communities will change during that whole time period. Then another 2 projects that I do are based on natural laboratories. And what that means is that we will use systems that already exist in the oceans to basically mimic ocean acidification. So I'll have field experiments, which is called in situ experiments, rather than having laboratory experiments. So I will not set anything up in the lab, but I will just do everything in the ocean itself. So the first one, so in a perfect world where you have a lot of money, you would of course try to combine both experiments to get the best research conclusions out of it. Okay, so the first one that I do is look at CO2 seeps. So what is that? That's basically carbon dioxide that naturally bubbles out from our ocean floor. So as you can see on the picture here, this is a CO2 seep site. So what we do is we take samples from a control site, and we would take samples from the CO2 site, and we see how the communities differ. And this CO2 site would then be our ocean acidification mimic, basically. And we'll have CO2 seeps at 2 different locations, one in Japan and one in the Dominican island. And so we will not only compare the communities that we found at the control versus the high CO2 site, but we will also compare the 2 different locations and see if that maybe has an influence as well. And then the last part that I do is make use of a kelp forest as a sort of ocean acidification environment. So what is kelp? Kelp are large brown seaweeds, and they're very productive ecosystems. They give shelter to a lot of different organisms. A lot of fish stay in those big kelp forests because they are protected from their predators. We use the kelp forests because they have a lot of daily pH variations, which is good for us because that's what we want as our ocean acidification experiment. So what I'll do is I'll take samples from inside the kelp forest, and then take samples along the way to the edge of the forest and see how those different pH variations that I see affects my bacterial communities. So that's a little bit of what type of experiments that you can do for ocean acidification. And then before I end, also want to discuss about what we can do to help ocean acidification. Well, the first thing is we can reduce our own carbon footprints. So our own little contribution of how to reduce the greenhouse gas emissions. So what you can do, it's very simple. It's trying to walk more, trying to take your bike more instead of taking a car. Never leave your lights on. Simple things like that, but it will have a big impact if everybody does it. And then also for ocean acidification, support the sustainable fisheries. Second part is to share your knowledge. This is what you guys have been doing for the past couple of weeks, so that's very good. Also, I hope you learned something today about what I just talked about. And another thing about sharing or raising awareness is the climate strikes that have been happening all over the world. A third thing that can happen is to support the science. So by supporting science, we can get more data out of ocean acidification, and we can use that information then to implement appropriate strategies to adapt, or proper adaptation strategies to deal with climate change. And the last part then is to protect our vulnerable societies. So like I said, the coastal communities or the island communities that will get into trouble if we get sea level rise, or if we get a lot of floods, or also people or communities that live in very dry areas, they will also have a very negative effects if we get these increased extreme weather conditions. And that's it for me today. So thank you very much, everybody, for watching and listening. And I hope you learned something. Any questions?
Okay, so any questions for Hannah? Feel free to turn on your microphone or feel free to drop the question in the chat.
Hello. Okay, so I'm seeing here one question as well in the chat, which is asks, is it possible to extract CO2 from the ocean in large amounts? No, the straight answer would be no, it is not really possible, because CO2 basically gets stored in the ocean. So as I said in my little example of the simplified food web, either CO2 basically cycles through all types of organisms which get used in their bodies, or it get used to build up the shells. If they die, that CO2 basically goes down or sinks down to the bottom of the ocean, where it just like stays there and becomes a part of the sediment. Because the ocean, the whole cycle that you get through the ocean happens for 100 to 1,000 years, where our ocean masses continue to mix, and some of the deeper water sometimes comes up into the atmosphere, but it takes a while for that to happen. So even though if we would stop our emissions today, ocean acidification will not directly stop from happening, because of that CO2 that gets stored into the ocean, and then in 100 or 1,000 years, it will come up again from the bottom, and it will still have an effect on ocean acidification. So the main thing that we can do to reduce CO2 in our oceans is basically to try and reduce our CO2 emissions into the atmosphere. So I hope that answers your question.
Well, we had a question. I don't know if you can hear me or not. So we're a fourth grade class. There are actually 3 or 4th grade classes in Kansas. We've been studying some climate change and effects on how it has on the ocean and sea turtles. So we've been studying sea turtles, and I know that your research deals with things at the very bottom, smaller organisms at the very bottom of the food chain. But how would climate change and increased levels of CO2 in the ocean affect larger animals like sea turtles and those organisms?
All right, thank you for that question. So the question was, how will CO2 impact sea turtles? It can happen, I think, in a couple of different kind of ways, where, so as I said, CO2 can affect, if CO2 levels will, or ocean acidification will affect the lower part of the food webs, then it can affect sea turtles by way of bottom-up control. So if these phytoplankton bacteria interactions, if those collapse because of ocean acidification, then the higher trophic levels, such as sea turtles that depend on those, will collapse as well. So that's what we call a bottom-up control, but it's not a certainty that that will happen. And for that to happen, ocean acidification will have to increase definitely first to actually collapse those phytoplankton and bacteria. But it can also have a effect on sea turtles in the way of, as I said, their internal biological balance. I don't know how huge that effect would be, or how much energy the sea turtles have to revert to deal with that internal balance. There probably be more indirect effects of ocean acidification on sea turtles than actual direct effects. So direct effects would be basically, because ocean acidification happens, sea turtles would die because they can't deal with the environment. but more indirect effects would be like the bottom-up control, or because sea turtles won't have their food source anymore because of ocean acidification. But the thing that you also have to keep in mind that ocean acidification is not a process on itself. Next to ocean acidification, you have the increased sea surface temperatures, and you also get the oxygenation of the ocean, and all of those factors will kind of sort of play together. So sea turtles might change their migration, they might change their habitat, because maybe in the areas where they're living, the oxygenation of the ocean will decrease. So maybe they won't have enough oxygen anymore, and they'll have to change their habitats to a different place where they'll have more predation from higher up organisms as well. So I don't know, I cannot give you a straight answer on how much the effect of ocean acidification will be, but it will, I don't think it'll definitely be a direct effect, it will be an indirect effect, and a lot of other climate change effects will play a part in that. I've also seen another couple of questions that have come up. And the question is, what is harmed the most from pollution? Is it the sea animals or coral reefs? If you talk about pollution, we all know, because it's been covered in the media pretty like heavily, that coral reefs definitely have suffered from pollution. But I don't know if you can say that coral reefs suffer from pollution most in comparison to sea animals, because if we take the example from the sea turtles again, I think all of you definitely have seen a lot of videos or a lot of pictures where sea turtles get strung up in fisher nets, or they get harmed by the straws that we have in the ocean. So I think both animals and coral reefs are harmed equally, or are at least harmed a lot from pollution. The thing is, the coral reefs are not just harmed from pollution, but they are impacted a lot by both the increased temperature and the ocean acidification as well, in addition to pollution. And that's why we see so much coverage of the harm to coral reefs in the media, because all of these impacts affect coral reefs the most, because they cannot deal, they have a very specific niche, so they need this very specific temperature to live in. So the increase of the sea surface temperature has a very big effect on the coral reefs. And then if you combine that with ocean acidification, that also has an effect on the coral reefs, plus the pollution, then you can definitely say that coral reefs are being harmed at a very high level. And in the future, there's going to be more decrease in coral reef. And then another question that kind of follows up on that is, it says, we see pollution on coral reefs, what can we do? Well, for the increase in sea temperature and the ocean acidification, the main thing is try to reduce your own carbon footprint, because those effects on coral are mainly because of the increase in greenhouse gas emissions that we have. So if we try to reduce our own carbon footprint, that will have a big effect on those coral reefs. As in pollution, well, it would be very nice if people would stop trying to get fossil fuels out of the ocean, if they would stop dredging as well, because all of that harms the coral reefs as well. If you dredge more, so if you take more sediment out of the ocean, that all creates kind of a turbid environment, and that makes sure, well, that affects corals, because it kind of clogs up the way they want to take up nutrients. So it basically makes them kind of starve. So there's a lot of ways that we could try and help coral reefs. So one would be to reduce your own carbon footprint. The other would be to try to increase the, or just participate in the climate strikes, which gives awareness to the coral reefs, and also definitely support the science, so we can do more research on it, and we can maybe try and create or nurture or trying to find ways to adapt the coral reefs to the changing environments. Some other questions that I've seen coming up. So at what rate is ocean acidification increasing? That is a very good question, and I don't directly have an answer for you that because I don't know the number by heart. But what I can tell you is that so we have seen, in comparison to the Industrial Revolution, which basically started in the mid-1700s, we have now increased the ocean acidification with 30%. So that is quite a lot. And it will continue to happen for the next couple of years. And they've also, if we want to stay below the increase of 1.5 degrees Celsius or stay below the increase of 2 degrees Celsius, that means that we will actually have to reduce our emissions by 16 to 33%. So that is quite a lot. So we will have to really make an effort to reduce our carbon or CO2 emissions in the atmosphere to actually help reduce our ocean acidification as well. But I'm pretty sure that you can find the rate of ocean acidification online. I'm sorry, I didn't specifically look up what the rate of increase is right now. Let's do one more question, or let's do two more questions, and then I'm going to call it a day for me because it's 3:30 in New Zealand in the morning right now. So the last question that has come up, how many species of fish are dying? I cannot give you a specific answer on that, but there have been, I haven't heard yet of a fish species that has gone extinct, but there are a lot of species or populations that are definitely declining. And if we keep continuing in the way that we are continuing now, so if we keep continuing with the emissions that we're having now, then definitely populations will become extinct. And maybe an example of ocean acidification, so some research that recently has come out is that they've studied the impact that the asteroid had on our Earth thousands of years ago, like 66 million years ago, when all of our dinosaurs basically died out. They now found some evidence of some phytoplankton where they can actually look at the ocean acidification event that happened because of the impact of that asteroid. And the ocean acidification that happened because of that event was an increase or a decrease in the pH of 0.2 units. And today we already have, remember, we already have a decrease of 0.1 unit. But that ocean acidification event then actually caused mass extinction events for a lot of species in the ocean. Of course, there were other factors that contribute to that, but we can now start learning a lot of the event that of that ocean acidification event that happened then, and try to take that information and study or apply it to nowadays situation and use it for projections into the future. So I hope that answers all of your questions, and I think that's it for me.
Okay, thank you so much, Hannah. So I was taking a look at the list of participants. We had people from Colombia, Honduras, India, Greece, Romania, Bangladesh, Canada, Catalonia, Pakistan, UK, Ukraine, South Africa, Italy, US, and probably more. And we all would love to thank you because we know that this is quite an effort, speaking in the middle of the night at 3 a.m. So I would suggest that all of you participants turn on your microphone and let's say thank you to Hannah and give her a huge applause.
Thank you.
Thank you. Thank you, Hannah.
Thank you.
Thanks.
Thank you.
Bye.
Thank you, everybody. I hope everybody enjoys the rest of their day and the end of your climate action project. Good luck, everybody.
Thank
Thank
you.
Thank you.
Bye-bye.
Have a great day.